This gives you Z. Okay? So X first, then S. That gives you Z, or Z. Right? Look, they're different. They're different. Now, for a group to be abelian, all pairs have to, when you commute them, have to give the same result. But these two don't. So if you commute XS, you get SX, but the answer is different. Okay, so therefore, this group here is non-abelian, right? It's non-abelian. Okay, so the question is, a non-abelian group, for example this one, can have a proper abelian subgroup. A proper, so it means smaller than the group itself. Proper abelian subgroup. Well, look, here's a subgroup. You know, the set is IRS. Now, is it abelian? Because if it is, then the answer to this statement is true. I mean, it is true. Because it's a subgroup. Now, is it abelian? Well, anything with I something is abelian, right? I mean, commutes. Now, how about RS? So RS is I. SR is I. So that commutes. All right. So this is a subgroup, and it's abelian, right? And it's a proper subgroup of this bigger one, and therefore we have found an example where a non-abelian group, the big one, can have a proper, so it's smaller than the big one, a proper abelian subgroup. This subgroup here is abelian. So the answer is yes, it's possible. And here's the example. That is a proper abelian subgroup of the big one. The whole thing is a group. So that's possible. So that's true. Okay. An infinite group cannot have a finite subgroup. An infinite group cannot have a finite subgroup. Now, whenever you hear the word not or all, a red flag should go up, and you start thinking, all I have to do is find one counterexample, right? So you start sniffing around for a case where the statement is not true, right? So, an infinite group cannot have a finite subgroup. Look, any group has two trivial subgroups, right? There's this one and itself. Okay. Now that is definitely it's a subgroup, right? It's a trivial subgroup, but it's still a subgroup, and it's finite, right? What does finite mean? A group that is finite means that its order, in other words, the number of elements it has, is finite. Right? It's not infinite. Well, this is a subgroup, and its order is 1, and 1 is definitely finite, right? So that's your counterexample. The trivial group is a counterexample. So the idea that an infinite group cannot have a finite subgroup is false, because that's an example of where this group G does have a finite subgroup. Right? So that's false. Okay, next one. An infinite, this one's tougher. Okay, an infinite proper subgroup of an infinite group must be abelian. Ooh, that's not easy. Okay, I'll say it again. Now, concentrate, right? An infinite proper subgroup of an infinite group must be abelian. Now, I really had to scratch my head for that one. Eventually, I got lazy and just looked up the answer. So, this is a tough one. And the answer was the following. When you see that word must, again, the red flag goes up, so you try to find a counterexample. And the counterexample that the book gives is the following. So your infinite group is the group of 2 by 2 invertible matrices. Okay, so you have matrices of this form, and they are invertible. We talked about this in the previous lecture. Now that's an infinite group, right? Now take a subset of that infinite group where the determinant of the matrix, so you take the determinant of the matrix and it's equal to 1. Remember the determinant is a number. You take a square array of numbers and you calculate the determinant using the linear algebra formula. I assume you've done some linear algebra. If you haven't, I will be giving a course on undergrad linear algebra a bit later. But for the moment I'm assuming you know about matrices and determinants and inverse matrices and all that stuff. Okay, so of this infinite set of 2 by 2 invertible matrices, choose a subset, and it'll be a proper subset, where the determinant of these 2 by 2 matrices equals 1. Okay, so and you can prove that subset is a group. Okay, therefore it's a subgroup, right? And it's a proper subgroup because the number of matrices where the determinant's 1 is a very special case compared to the general case. So it's definitely a proper subset. And it's a group, therefore it's a proper subgroup. Okay? An infinite proper subgroup, that's the set of matrices whose determinant is 1. An infinite proper subgroup of an infinite group, well this is an infinite group, okay, must be abelian. So all these matrices here, whose determinant is 1, must be abelian. Ooh, now you're talking about matrices, right? Now the binary operator for matrix just multiply 2 matrices together. That's the binary operator, just a matrix multiplication. Now in general, 2 matrices like A and B, in general, a matrix A times matrix B is not the same as matrix B times matrix A. Typically, it's only in special cases that matrices commute, right? Most times matrices do not commute. So these matrices here with determinant 1, they are a proper subgroup of this infinite group, okay? And they are in general not abelian, right? Because they're matrices, okay? So therefore, this statement, an infinite proper subgroup, the set of these with determinant 1, for example, of an infinite group, this is infinite, all these 2 by 2 invertible matrices, must be abelian. Well, no, they're mostly non-abelian, so that's false, okay? All groups have proper subgroups. Well, that's obviously false, right? Because consider the trivial group, just with just one element, order 1. Okay? Does it have a proper subgroup? No. So therefore, all, you see that word all, the red flag goes up. All you have to do is find one counterexample, and that statement's false. Okay, well here's a really trivial example. That has no proper subgroups. You can't have a subgroup of this that's smaller than group of order 1. Right? That's the smallest. That's why it's called the trivial group. This group is the smallest group. There's nothing smaller, right? Okay. All right, now the last one, and I will stop for a minute and clean the board, because I think this is a better way actually than just me cleaning it on film.